Hey guys, I hope your Sunday's going well. I've decided to make this next unit two videos instead of putting so much into one video. The unit's called Stars and Galaxies. We're going to explore um, the point after the universe has expanded and look at a star today and see what's happening inside of stars. Here are your 4 learning targets for just this video. There'll be some more learning targets for the next video. So stars are born from interstellar clouds of dust and gas called nebula. And this gas is mostly hydrogen gas, and then the dust is basically remnants of leftover debris from exploding stars in the past, and other debris left over from the Big Bang. Um, so these clouds of dust and gas, as they continue to grow, they eventually start to, like all things, they start to succumb to gravity. Gravity starts to win, and the gravity, as the cloud gets more massive and more massive, begins to pull material in towards the center of the cloud, and the cloud slowly begins to spin. And when this happens, this pulling in of gravity, the center gets very, very dense, and with this increase in density comes an increase in pressure, and as pressure is driven up, so is temperature, because when things are squeezed or under pressure, the temperature increases, and it increases to the point where fusion begins, which is about 10 million Kelvin they have measured in stars today. So at about 10 million Kelvin, hydrogen nuclei start to fuse into helium nuclei. Now, we've already talked about that back in unit number 1, so I thought we'd just revisit it. And when this fusion begins, that's when the star basically forms and takes shape and starts to glow, and we can say a star is born. Now, obviously stars aren't alive, and stars technically don't die, but the term a star life cycle is sometimes used because we watch a star from its creation to its end, and that's kind of like a life cycle. So once a star ignites and starts to fuse hydrogen into helium, this is called its main sequence stage. And most of the stars in the night sky that you look up and see are in their main sequence stage, as is our sun. Our sun is very much a average star in both temperature and size, and it's one of a very common number of stars its size. There are stars less than its size and stars more than its size, but it doesn't really matter how big or small the star is. All stars go through a main sequence where they're converting hydrogen into helium. Now, when a star is doing this, there's an equilibrium, an equalization of forces. So helium, when it throws out all of its light and all of its energy and all of its radiation, that outward force is pretty powerful, but the force of gravity is just as powerful. And the force of gravity inward and the force of fusion outward, the pressure, equals in a star is said to be in equilibrium as long as it's in its main sequence. So if you look at this next to the last bullet, stars range in size from 1/10 the size of our sun to sometimes 100 times the mass of our sun, and the diameter becomes even greater than that in some situations. And we'll look at the great big stars in the next video. Main sequence stars are classified. How do we classify them? They're classified by 3 ways: their color, a letter, which we'll explain in a minute, and temperature. So there's the letters. They're called the spectral classes, and they're based upon elements, the spectra of elements that are observed in certain size stars. Our sun is a G-type star, and each spectral class, because there's so many stars and there's just 7 letters, each spectral class is subdivided of a range from 0 to 9, basically 10 digits. And in each spectral class, let's say the example here, our sun's a G2 star, the number 2 actually means it's hotter than a G3. So from 0 to 9 in any class, for example, an A5 star is hotter than an A9 star. An A9 star is actually closer to F, and an A0 star is actually closer to B. So the number, the lower it is, the hotter it is on that scale within that class. So what happens when our sun runs out of hydrogen? Well, our sun is not big enough to do some of the more spectacular end-of-life events that some other stars that we'll look at next video do. Um, Basically, what's going to happen when our star runs out of hydrogen is the core of the star will start to contract. And as I said before, this contraction, this pressure, will drive the temperature even higher, high enough to fuse helium. Remember, all the hydrogen was fused into helium. Now it's a big ball of helium. When this helium, when the core becomes hot enough, the helium will initiate fusion again, and this will cause it to turn into or fuse into carbon. Now, as this happens, or right before this happens, because the pressure of the gravity inward, the force of gravity inward is now more than the fusion outward because it ran out of fuel, gravity will take over and the star will collapse and bounce off the core. All the energy will bounce off the core, and the star will expand outward greatly and become what we call a red giant. Now, a red giant is many, many, many times greater in diameter than the star that it used to be. And in our solar system, scientists believe it will take up the orbits of the inner planets. So Mercury, Venus, Earth, and Mars will be consumed by this growing red giant. So when this red giant expands, all the other material in the star will be blown off, and what we have left is this is after the star runs out of helium. I'm sorry. So the helium will still fuse into carbon. The star will glow as a red giant, and when this red giant runs out of helium to fuse into carbon, our star is not massive enough to do the next fusion phase. It can only do 2 phases of fusion. At this point, all the material is going to be blown off because once again the star is going to collapse on itself, and the core. Remember, now the core is carbon. Not enough mass to initiate the fusion of carbon into the next element. So what happens is the core remains as carbon, and this star is no longer producing energy, but it's still very, very hot, and it's called a white dwarf. But it's not doing fusion. It's just a white dwarf in space that slowly and very slowly, measured in billions of years, cools down. Now, hypothetically, it will cool into what they're calling a black dwarf, but so far they've not found any black dwarfs in the galaxy. They have found white dwarfs that are as cool as 3,000 Kelvin and continue to cool, but right now the universe is not old enough to where they actually have found evidence of black dwarf stars, but they're getting there, so that's why it's called hypothetical. Okay, that's the end of video 1. Be sure that you take notes. If you have to, go back and look at it again. You can always turn the sound down if you don't want to hear my lovely voice again. But take notes, because some of you aren't doing very well as far as studying, and I think that's because you've been a little bit lazy and thought that you could just memorize things as they happen on the video, watching it one time. But as your test scores show, you can't do that. So please, please, please take notes. Thank you.